Hello students, let me continue with the last part of the chapter Chemical Bonding and Molecular Structure. The last part has two concepts, hybridization and molecular orbital theory. Before I start, I would like to remind you that these concepts are discussed already for the first PUC B division students and pending for the A division students. So other students can take it as a revision class. Let me begin with hybridization. To understand something about hybridization, you should recollect about the different shapes of atomic orbitals, types of atomic orbitals and their shapes, which I have already discussed in the previous class. As you all know, students, that sp, d, f orbitals have different shapes and hence different energies. A chemical bond is formed between two atoms when orbitals with identical energy and similar shape overlap. To attain this, the atomic orbitals undergo a process called as hybridization. Hybridization is a process of mixing of two or more atomic orbitals of different energies, particularly in the valence shell of an atom, to form same number of orbitals, in particular identical orbitals having equal or equivalent energy. So this is the definition of hybridization. It is a process of mixing of two or more atomic orbitals having different energies in the valence shell of an atom to form same number of identical orbitals of equivalent or equal energy. To understand this definition, we will be discussing the types of hybridization. The first type is sp3 hybridization, and the example considered is methane molecule CH4. The central atom in methane molecule is carbon. Consider the ground state electronic configuration of carbon, atomic number Z6, as 1s2, 2s2 and 2px1, 2py1, 2pz0. When carbon in the ground state absorbs energy, it jumps to the excited state. Now, in the excited state, one electron from 2s atomic orbital jumps to the vacant 2pz orbital. Now, there are four unpaired electrons as you all see there. Therefore, carbon atom is tetravalent. Now, to make this concept much more clear, I have considered the energy level diagrams. Look to the carbon atom in the ground state and the energy level diagram. 1s orbital completely filled, 2s completely filled, 2px, 2py, 1 electron each, and there is a vacant 2pz orbital. When carbon absorbs energy, it migrates to the excited state in which 1 electron from 2s orbital jumps to the vacant 2pz orbital. 1s and 3p orbitals, 3p orbitals and 1s orbital, they undergo hybridization to form 4 sp3 hybrid orbitals. This is the carbon atom in the sp3 hybridized state. So there are 4 sp3 hybrid orbitals which have equal energy. In case of methane molecule, if you consider methane molecule, look to the structure as shown here. Yes, each carbon atom is having 4 sp3 hybrid orbitals which are directed to the corners of a regular tetrahedron. These sp3 half-filled hybrid orbitals overlap with 1s atomic orbital of hydrogen atom along the axis to form sigma bonds. So the molecule assumes a tetrahedral shape. Now if you look to the shape here. So each sp3 hybrid orbitals 1:3 ratio is that of S and P. Hence it will be having 25% S character and 75% P character. So bond angle is 109 degrees 28 minutes. That is the normal tetrahedral bond angle. So this is in detail regarding the sp3 hybridization of methane molecule. I hope this is clear. The second type of hybridization is sp2 hybridization. And to explain sp2 hybridization, the example considered is that of the first member of alkenes, ethene. The molecular formula is C2H4. Once again, we need to look into the ground state and excited state electronic configuration of carbon, which remains the same as in methane. So again, we'll be considering the energy level diagram of ethene molecule carbon atom. So ground state configuration remains the same once again. Vacant 2pz there, if you look, it is vacant. So after absorbing energy, carbon in the excited state will have 4 unpaired electrons. So out of the 3 2p orbitals, only 2 are involved in hybridization. 1 yes and 2 out of 3 2p orbitals mix. This remains unhybridized. So that you will end up with 3 sp2 hybrid orbitals. Look to the carbon atom in the sp2 hybridized state. There is 1 electron in the unhybridized 2pz orbital which has different energy as indicated in the energy level diagram. Now this is to be considered for the 2 carbon atoms of ethene molecule. Each carbon atom is having 3 sp2 hybrid orbitals. If you take this carbon atom, it is 1, 2 and 3 sp2 hybrid orbitals. Similarly for this carbon, it is 1, 2 and 3 sp2 hybrid orbitals. sp2 hybrid orbitals of both the carbon atoms overlap along the axis to form sigma bond. Each carbon still has 2 sp2 hybrid orbitals which overlap with the half-filled 1s atomic orbital of hydrogen to form sigma bonds. So totally here there are 3 sigma bonds. The other side, the remaining 2 sp2 hybrid orbitals similarly overlap with the 1s atomic orbital of hydrogen along the axis to form sigma bonds. In all, in case of ethene molecule, there are 5 sigma bonds. Now coming to the unhybridized 2pz orbital, the shape of 2pz is dumbbell. One half lobe is above and the other half lobe is below. Now similarly, the other carbon atom also has a dumbbell shaped 2pz orbital. Now the lateral or sidewise overlap of the 2pz orbitals results in the formation of 1 pi bond. If we look to the molecule here, totally there are 5 sigma bonds and 1 pi bond in case of ethene molecule. Now coming to the percentage of S character and P character, 1:3 ratio. Yes, so it will be 33% S character and 66.6% P character. And remember, for sp2 hybridized carbon atom involved in the formation of the bonds, the bond angle is 120 degrees. So this is in detail regarding sp2 hybridization by considering ethene as an example. Now the third type of hybridization is sp hybridization. To explain sp hybridization, the example considered is that of ethyne molecule C2H2. So the ground state and excited state electronic configurations remain the same. Just look to the energy level diagram here. Vacant 2pz orbital in the ground state, and in the excited state, an electron from 2s jumps to the empty 2pz orbital here. So for sp hybridization, only 1 out of the 3 2p orbitals mix with the 2s atomic orbital. So how many sp hybrid orbitals should be formed? 2. 2 atomic orbitals combine, 2 hybrid orbitals. So you will, if you look to the carbon atom in the sp hybridized state, there are 2 sp hybrid orbitals and unhybridized py and pz orbitals having different energies. Yes, so this is something about the energy level diagram. Coming to the molecule ethyne. the two carbon atoms. Each carbon atom is having two sp hybrid orbitals. This carbon also has two sp hybrid orbitals. Sp hybrid orbitals of both the carbon atoms, they overlap along the axis to form a sigma bond. The remaining sp hybrid orbitals of both the carbon atoms overlap with the half-filled 1s atomic orbital of hydrogen along the axis to form sigma bond. So totally 1, 2 and 3 sigma bonds are there in ethyne molecule. So as I have indicated in the energy level diagram here, there are two unhybridized orbitals py and pz. Both are having dumbbell shape. Just look here. So this is the 2py orbital and this is the 2pz orbital of one carbon. Similarly, this is the 2py orbital and 2pz orbital of the other carbon atom. Two py orbitals overlap laterally or sidewise to form one pi bond. Similarly, two pz orbitals half-filled overlap along sidewise to form another pi bond. So, in all, there are two pi bonds in ethyne molecule. If you look at the structure here, totally there are 3 sigma bonds and 2 pi bonds in ethyne molecule. And the bond angle is 180 degrees, which indicates that it is a linear molecule. So what should be the percentage of S character and P character in sp orbital? Sp hybrid orbital has 50% S character and 50% P character. 50% S character and 50% P character. So this is regarding sp hybridization. If you understand these many details regarding definition and types of hybridization, the other parts become easier for you all to understand. There are other examples also, you can just go through in the textbook. Now I hope this concept is clear to you all. Let me move to the last part, that is molecular orbital theory. Thank you.